Thank you very much for the kind introduction, and thank you for inviting me to this conference. So, after 2 more experimental talks, I would like to give a bit more theory insight, also about mainly magnetic skyrmions, and also about the dynamics. So first I will give a brief intro to magnetic skyrmions and the skyrmionHall effect, which we have heard about already. And there are many ways to get rid of the skyrmionHall effect, and I will show some of them, but I would like to highlight also one that we've been recently working on. Instead of building tracks by building the material, we can also just use magnetic structures to build tracks, and also I will show how to create, at least in theory, a protocol for creating skyrmions in these magnetic tracks. This is a work done by my student Ross Knappmann, Davi Rodriguez, who's now in Italy, and Jan Marcel. And in a second part, I would like to show that actually we can also have a non-zero skyrmionHall effect even for topologically neutral or topologically trivial magnetic structures. That's a work done by my student Robin Misiska, David Rodriguez, and Jonathan Lilliard from the MUMAX team. So let's start simple, a short review about magnetic skyrmions. So there were theoretical predictions quite early on by Bogdanov and Jablonski. The first experimental result was finding skyrmions in the form of a skyrmion lattice, where you see a neutron scattering picture here. And what you need to have to get skyrmions is you need to have broken inversion symmetry. This you can see by going through the skyrmion structure. If you go from left to right, you need to go from up to down. This you can either do by rotating to the left or by rotating to the right. So the inversion symmetry you can break spontaneously by just having it broken, or you can break it explicitly, like we have seen in the results when we use, for instance, Jalushinsky-Maria interaction, where the material itself breaks inversion symmetry. Skyrmions by now have been found in many different magnetic systems, including metals, semiconductors, insulators, in bulk and thin films. And also what has been a huge advantage to the field is that we have them above room temperature. So these first ones were below 30 Kelvin. Their size can be engineered, and all of them, at least from the theory side, can be traced back by having one interaction scales that would like to have them aligned, and one interaction scale that would like to have the canting. So when you go around the circumference of the skyrmion, it's just up, and when you cross it, you need this canting. And whatever interactions you find, you can then try to get these skyrmions. You can detect them by various experimental techniques, as we have seen in the 2 previous talks, and they occur in systems that are device relevant. We can create them, manipulate them, and also destroy them by different means, by electric currents, magnetic fields, and so on. And there's more than just the skyrmion texture, as we've been also seeing this morning. So there are more structures around. So what makes skyrmions cool? Well, they can be, oops, never this button. Okay, please could you? You didn't do it. Yeah, never this button, but I got lost. But I can still continue to talk until we get it fixed. So they can be rather small, and because of their topology, they are a bit more stable than other structures. So by a skyrmion, they belong to the homotopy group pi2 of S2, and you can map them to a sphere. So we are back, thank you. So this is the picture I was alluding to, so you can map a skyrmion onto the sphere. And something that makes the field also quite interesting is that they react to electric currents. So this is an early study we have done during the time I did my PhD thesis, where we found that in particular in the lattice form, they react to very low electric currents, like 5 orders of magnitudes lower to move domain walls. Unfortunately, that's not fully true for single skyrmions, but still this also pushed the field. So let's, from a theory point of view, now it can't click. Let's, from a theory point of view, let's look at the forces that act on a skyrmion from a general point of view. Basically, there are 3 types of forces. One is pinning forces, which just occur whenever the structure is stuck. Then the electron can move, and the video is not working. Okay, we checked yesterday, but now it's not. And the next ones are dissipative forces. So when an electron moves across the structure is just pulled along the direction of the current, similar to when you're on a boat, the boat just gets, along the water current traced. But there are also these Magnus forces, and these Magnus forces are then responsible for the skyrmionHall effect, because similar to a ball that's twisting around its own axis and then leads to these banana-shaped soccer ball curves, also these skyrmions feel deviations from the current direction. So these are the three fundamental ingredients, and they then lead to the skyrmionHall effect, which has been observed in different types of measurements. Even in a topological Hall effect, you see the respective electronic picture, and also in real space. So as we have also seen, the skyrmionHall effect is also not really cool for applications such as the skyrmion racetrack memory, so people work a lot on how to then get rid of the skyrmionHall effect, because if they move too fast, they would eventually get destroyed at the boundary. So how do we eliminate the skyrmionHall effect? So here are lots of studies, and there are a lot more. These ones shown work on two principles. So the left ones work on the idea of using spin transfer torques, and the idea that you have two opposite winding numbers. So I'm going to come back to that later again. And the right-hand side uses spin orbit torques and an additional symmetry breaking. But I would like to show that there's another option to these ones, namely to kind of not allow this drifting motion, to just confine these skyrmions to tracks in a natural way. So we want to build just these helical faces, and if I look closely to one of your movies, actually it looks like you have them. So we have these helical tracks. This one was not me, I pushed the lower button. So we have these helical tracks, and that's what I would like to explain. So let's start by looking at the helical state. So what are the ingredients for the helical state? We take exchange interaction, we take Joloshinsky-Maria, and we take a uniaxial anisotropy along the y direction, and then we get these helical stripes. And the nice thing about theory is you can do whatever you want to do, so we can rescale it to an effective one-parameter theory, which here is just dependent, so all of them have no constant in front, and we just have one kappa here. And this kappa has now all three material parameters, namely exchange, anisotropy, and DMI strengths. So just as a function of this kappa, we need to see what we can do. And we see if we make kappa large, then we have a strong anisotropy, so everything wants to order ferromagnetically. But if we make this kappa small, we get a helical ground state. So now, as a function of this kappa, we can study the wavelengths of the helix. And if we have kappa equal to 0, we have lots of helices. If we increase kappa towards this kappa critical, these stripes get larger. And what we also see is that the profile changes, so the profile from a smooth one changes to something where it abruptly changes. So, but in these helical phases, we can have several distinct skyrmion states, in particular two. One of them is that we take these stripes, bend them, make a hole, and put a skyrmion inside. And rumor says they have been also experimentally observed. And another option is that you take those objects, split them in half, and now it's working cool, and then extend it to the helical shape. So when you have kind of your stripes and you have a gap in them, this is also a skyrmion. So it has the same winding number. And these kind of like closings between these things, you can just move nicely. When you look into the literature, actually these ones, when you just compute these models, as we did and also previous study did, they are energetically the ground state. So they are lower in energy than these interstitial skyrmions. Okay? So now we can nicely move them, so we can apply current and we drive them. We can also do it with the second one, we just move them. And when we perform a TILA analysis, then what we see is that whatever we do, we just get a current, or we could just get the drive along this track. So what we need to do for this is, of course, kind of pin these helices, but very often when I have these large stripes, they are anyway pinned. And even when I apply current along the y direction, I still get a motion along the x direction. So that's cool, because as a theorist, we now have two tools. We can apply current in x direction and y direction, so I have two independent tools, and I can do different things with them. So what is also nice, if we look at the speeds, so we can compute the speeds as a function of the applied current density, and we see that we can move them with, in theory, 90 meters per second about, and then we can move both of them. Sure. They also start to deform. So if we apply more and more currents, then they start to deform. So this one, this Dij, is kind of like an information of how much they deform. And what we see is these interstitial skyrmions, because they feel the pressure from these two lines, they don't deform so much. But these ones, they have more tendency to deform. The other thing that we see, which is really cool, is that we can tune the speed not only by applying the current differently, but by looking at a material that has a low damping. So the damping here goes in as 1 over alpha. So if we kind of have a low damping material, then we can nicely increase the speeds. So as a function of increasing current strength, there are lots of things that happen. We have a pinning velocity, below which the texture remains pinned. If you just do theory and you have a super clean sample, this one is 0. If we go a bit higher, we go into a moving regime where these structures nicely move. But the higher I go, they start to deform. And if I go even above this VC, which I call also, if I go very high, I destroy my long-range order. But if I go in this middle, then actually I can produce skyrmion-anti-skyrmion pairs, because then these deformations are so high that I can create these skyrmion-anti-skyrmion pairs. So hopefully the video works. So what you see here is the current strength as time, and we increase it. And what you're going to see here, we have put some sort of impurity with a higher anisotropy strength, and now it starts to deform around this impurity, and then we start to see these H-shaped skyrmions here and an anti-skyrmion here. So in case the movie didn't work, I just put a picture series here, and below you see the winding number structures. So you can see that in the end we have something purple here, something green here, so one has a positive, one has a negative winding number. So we have a skyrmion and an anti-skyrmion created. Unfortunately now our impurity looks a bit stupid and not like at the beginning, so we need to have some sort of idea on how we restore it. So therefore we came up with kind of a protocol on how to create, restore impurity, and create another one. So we have now the advantage that we can apply currents in X direction, shown here in blue, and the green ones are going to be the current in Y direction. So first we did a pulse, and we end up with this image. Now we apply current in Y direction, which allows us to move the skyrmion away. And we didn't just consider this one, but you could also work with the one on the other side. And then we can apply a strong pulse, even throughout the texture, where we can restore the impurity, and then we can create another one. So I just talked about these helical tracks. Let me come back to the other two ideas. And more importantly, because here you see this W, which is related to the skyrmion winding number, but here you don't see it. So also to the question, what is the role of topology in the skyrmionHall effect? Because this has been very much debated. What does topology actually mean? If you look at the LLG equation in a very general form, you see how the magnetization changes over time, and we can add torques here. And we have seen that there are different types of torques, spin transfer torques, spin orbit torques. So let's start with spin transfer torques. If I do spin transfer torques, and I just do a very simple calculation to see the basics of the core ideas, and we do a Taylor ansatz of just a rigid moving structure, which we can just plug in, and then we get an effective equation of forces, which are the forces that I explained in the beginning. So we see gyrotropic forces, the Magnus forces, dissipative forces, and pinning forces. If we neglect pinning for the moment in the moving regime, then we can solve this object. And this G here has the skyrmion winding number in it. So here we have directly the topology entering. So if we look at the skyrmionHall angle, which we then can compute, it has the skyrmion winding number. So let's look at this equation. And it vanishes for structures that don't have a topological index. So it's also independent of whether you're Bloch, Néel, or something in the middle. So it's just independent of the helicity of the skyrmion. It changes sign when you go from plus to minus winding number, because here it's quadratic, here it's linear. So if you do up or down skyrmion polarity, it has a different sign. So this gives you one recipe to eliminate the skyrmionHall effect. Okay? How? You take one skyrmion with plus winding number, you take one skyrmion with minus winding number, you apply current. Each of them would have a skyrmionHall effect in a different direction, but if you couple them strongly, then they move straight. So this coupling strongly you can do in different ways. You can just do synthetic antiferromagnets. You can do directly making them into each other by having antiferromagnets, or you can do a skyrmionium where you basically extend one skyrmion and put another skyrmion inside. So spin-orbit torques, let's look at them now. So with the previous one, we saw the winding number is a key part. So now let's look spin-orbit torques. So spin-orbit torques, if we do the TILA analysis, we can also compute the skyrmionHall angle. What we see, it does not simply change sign when we go from plus to minus, because we have these other terms here. So what we see is if we have a plus and a minus polarity, we do get an asymmetric Hall effect. So one of them would, for instance, move a little bit only, and the other one would move a lot in a different angle. It also depends on the helicity of the skyrmion. So here we have a difference whether we are Bloch or Néel. So for Néel, actually they move rather straight. For Bloch, they move perpendicular. So this also gives us a recipe of how to get rid of the skyrmionHall effect. Namely, we just tune the helicity such that these two effects compensate each other. So these are basically these two types of effect you can play around with. So spin-orbit torques, spin transfer torques, and the idea that you have these opposite topologies, and spin-orbit torques where you use an additional symmetry breaking, and I just explained this upper right one. But what is now nice is that you can do a very simple equation, 0 plus 0 is non-zero. So what do I mean by that? You can try to combine these two techniques to actually get a skyrmionHall effect now for a topologically trivial structure. So let me explain this. So, oh, nice. Okay. So now we have these two winding numbers with a strong coupling, and if we use spin-orbit torques, we will see that we actually get a deviation. So we will get a non-zero skyrmionHall effect, even if we have two opposite winding numbers. So in this, the idea is that the forces on the top and on the bottom skyrmion are not the same. So they therefore don't cancel the perpendicular components. And this you can realize in synthetic antiferromagnets, in antiferromagnets, or also for the skyrmionium. So from the theory side, what is nice, and also the skyrmionium really is something that is a topologically trivial structure. What is nice from the theory side is that you can describe everything on the same framework. So we can just do one TILA analysis by having two skyrmions with two different radii, where we can do the same thing also with the skyrmionium. So you have an inner skyrmion and an outer skyrmion. And then you can look at all these individual terms that enter, and what you immediately see is that this G here is plus and minus 1 for each of them, so it cancels overall. Okay? And all the other terms are remaining, so you can get a net skyrmionHall effect. So the topological part vanishes, but in the simplest case, so of course we computed also the long expression, but I just want to show this simple case where we have the two radii equal to each other, then the skyrmionHall angle is just proportional to the helicity. So this we also confirmed by micromagnetic simulations for the case of the skyrmionium and also the synthetic antiferromagnetic skyrmion. So how do we obtain twisted skyrmions? I think you have them even in your materials, not only Bloch and Néel. DMI is kind of the key ingredient. If we just kind of mix what is called interfacial and bulk DMI in the community, then we get these hybrid types of DMIs. Or if we have dipolar interactions, and well, the naive idea would be to take a non-centrosymmetric crystal and have something with strong orbit coupling below, then you get interfacial and bulk DMI. or you just look immediately into crystals, because that's just a reminder. These ones appear because the crystal or the system itself has a certain symmetry class, so you can also try to look into systems which have the corresponding symmetry class. So other options that were also shown in this conference were to kind of change the DMI, oxygen-induced DMI, voltage-controlled DMI, and so on. Magnetostatic interactions play a role because they favor Bloch. But what is interesting for us is that it's independent of the source of where you get this helicity from. So the effect, at least in theory, remains, and then you should get this non-zero skyrmionHall angle. And since we are no longer talking about something with a topology, maybe we need to think about whether we still call it skyrmionHall angle. So with this, I'm at the end of my talk. I told you two stories. One is that we can create skyrmions in the helical phase by providing natural tracks. That we can have a non-zero skyrmionHall effect for topologically neutral structures. And I would like to acknowledge the funding, thanks to my team and our collaborators, and for my family for the support to be here. Thank you very much.
Thanks for the nice talk. I wonder about the first topic you covered. Mm-hmm. There you have a nice direction of the stripes of the helical state. But if I saw it correctly, you have a DMI which allows several directions of the helices at the same time. Mm-hmm. So would you expect, I mean, in a real material, you can have different directions or grains with helices in different directions. So then you will find objects going anywhere. How do you solve this problem?
So what we do in our model, we also have an in-plane uni-axis. So we have an MY. I'm trying to go back, but it's not so easy. So what we take in our model is we have like this in-plane anisotropy. And this favors these structures being aligned in the Y direction. So the color code is here such that I think black is into the plane, white out of the plane. And then green is along the Y direction and purple is along the Y direction. And if I go a little bit more back, no, that's forward. Okay. So what we saw is that these stripes get wider as a function of this kappa here. So as the function of this in-plane anisotropy, these stripes get wider, so we want to be more green and more purple, and therefore that's our direction. And yes, if you have lots of grains in your material, you can also have these, but what you need for it to work is that you have really orientated stripes.
Thanks, but do you have any material that it's around these parameters?
Well, I think these things actually have been observed by now, so, but...
Thanks.
Yes, so I was wondering whether you consider spin transfer torque driving as a fact in experiments, or if there is any strong evidence that this is occurring.
You mean here?
No, so you analyze the different type of Hall deflection for the two driving mechanisms. So there are systems where the main wall motion driven by spin transfer torque is very relevant. So is that the case also for skyrmions, or?
I had the feeling that the original works were spin transfer torque and spin orbit torque appeared later.
Yeah, but I mean, your feeling now, if you sort of look at the literature, what would you consider as the most relevant?
Of course, spin orbit torques are more effective, and that's right now because you make it a little bit faster, more efficient. That's the way to go from the experimental side.
But so, for example, you cannot distinguish whether you have a component, so both mechanisms acting at the same time by looking at the whole angle, for example.
Yes, so our idea for the theory was that a lot of people think, okay, we have a topologically protected object and it is the only thing that leads to the Hall effect. So what we wanted to do is we wanted to individualize the effect and lead it back to the basic model, because with all the effects that you want to suppress the Hall effect, it's actually very difficult. So especially the things where you just have plus and minus winding number, when you just lead to a synthetic antiferromagnet, the two layers are not identical. But even if you make them fully identical, then there are ways to still get a Hall effect, and so on. So this is what we wanted to point out. That was our motivation, to look like even if you have a very clean system, can you suppress it or not suppress it? And what is kind of the effect that always goes into the theory? That there are more effects? Sure.
Thank you.
It's more a comment and related to your question, Pietro. In fact, even for domain walls, the old style spin transfer torque can be very efficient. We demonstrated a long time ago that we can reach in magnetic two-line junctions domain wall velocity up to 500 or 600 meters per second for similar current density. But what you said this morning, that the nice thing with spin orbit torques is that you have naturally the good symmetry. You don't have to create complex MTGs, whatever. And this is, I think, okay. But the old let's say, spin transfer torque is also very interesting.
No, sorry, just because I showed the other day, I think you weren't here, that in manganese nitride, the old spin transfer torque, in fact, works very well. We are trying to. But at the moment, we have no DMI. We try to induce it by putting a heavy metal on top, but we are not ready for that yet. And then I had another comment on, we had a paper published in 2020 on C2V film with C2V symmetry, in which we show the presence of in-plane anisotropy, which induces a DMI anisotropy, and we have these stripes in which they are very similar to your system.
Thank you.
But actually, in order to have skyrmions, then we need to apply a field, and so we destroy the stripes. Yeah.
You said that a skyrmion two one inside another, would like each of them would have a different parallelity in this case to move in the direct path, or if you take the same material and just create a skyrmionium, would these two cancel each other or not?
So you mean the winding number?
Yes, so you have two like
No, you keep rotating.
yes, you keep rotating, so you have the same
So the winding number, if you just compute them, they're opposite.
yes. Okay. But then they would give rise to different length.
Yeah, but they are strongly coupled, so because they can, one cannot move out of the other, so each of them feels kind of this force to go away, but if they are strongly coupled, then they can only go straight.
And then to realize of the material and experimentally.
So skyrmioniums are observed.